Hi, and thanks for joining me. Today we're going to be doing a video inside a fossil fuel power station, a coal-burning power plant to be more accurate. My name is Ryan Jackson. I own Ryan Jackson Electrical Training. I make my living traveling around and teaching seminars on the National Electrical Code, and I've had the great fortune of teaching at this facility that we're going to be touring for several years now. And I have to admit, it's probably my favorite place to teach. It has some things in it that are just extraordinary, and I think you'll enjoy this a lot. My website is right there, and my email address if you need to get a hold of me. If you have any questions, comments, please don't hesitate to get in touch with me. So the place that we're going to be taking our tour of today is the Intermountain Power Project, IPP power plant, and that is found in Delta, Utah, which is pretty much central Utah. Now, just a couple of things before we get too deep into it. I want to make sure that we're clear on this. No sensitive or secure information or photographs are going to be shown or discussed. We're really going to go behind the scenes of this power plant, but there are certain parts of the plant that even I'm not allowed into. The main control area, anything having to do with cybersecurity. The Department of Homeland Security, for obvious reasons, doesn't allow anybody inside of certain areas of the power plant. So there are areas that we're not going to be able to see, but I think you'll be surprised at just how much we are able to look at and discuss. So a general overview of the project. It's a 1900 megawatt capacity. It supplies one 500,000 volt DC line that goes for about 490 miles down to Southern California. My understanding is that this power plant provides about 20% of all electricity used in Southern California. So it's obviously a substantial amount. It also supplies a couple of 345 kV lines for 50 miles to a small town in Utah called Mona, and also one 230 kV line that goes for about 140 miles to a place in Nevada. I don't recall what city it is. It uses about approximately 5 million tons of coal per year, and we'll go through how it does that. That's about 1.2 million pounds per hour. When it's going at full capacity, it burns 1.5 train loads of coal each and every day. That's not 1.5 train cars, that's 1.5 trains with 100 cars on each train. So it can burn about 150 cars of coal in one day. Once they thaw out the train, which we'll talk about, it takes about 16 seconds for them to unload a car full of coal, which is just remarkable. We'll also talk a little bit about the boiler, and I wish that I could show a picture of the boiler because it's just staggering how massive it is. You really can't do it any justice. You can't take a picture of it because it's so big that it would never fit in your camera. It weighs 20 million pounds and can hold 347,000 gallons of water. And what is really stunning is that it's suspended in the air. It's inside the building, and it's suspended as a way to protect it against seismic activity. So here in Utah, we are in what the building code would call a seismic design category D2. So we have to worry about seismic and earthquakes, and one way that we can do that is to hang stuff from the ceiling and let it move around in the event of an earthquake. All right, so we're driving into the power plant, and the first thing that we see is the sign here that tells us where we're going, the Intermountain Power Project. And that's what it looks like. So up here we have the chimney. It's 701 feet tall, and then inside of here is where all the magic happens. Here you've got the generator, the boiler. Off to the left is what's called the switchyard, and we'll have some better pictures of that here in just a minute. The transformer that supplies the switchyard is just amazing, and we'll show pictures of that as well. This is an aerial photograph. I didn't take this. This is just off of their Wikipedia page. What we just looked at is this portion of the photograph, and that, of course, is the chimney. Over here to the right are a couple of cooling towers, and that's not smoke coming out of those. That's just steam. So in the winter, when it's quite cold, it seriously looks like the place is on fire. When you drive up to it, It's shocking how much what you think is smoke is coming out of it, but it's not actually smoke, it's steam. So most of what we can see here is actually just steam, water vapor, whereas some of it is in fact smoke. Okay, so this is a coal-fired power plant, and we bring in trains full of coal. So this is in central Utah. It gets cold in central Utah. So what do you do when you have a train full of coal that is completely frozen? You can't unload it. You have to drive it through what they call the thaw shed, and that's what this guy here is. This is the thaw shed. You bring a frozen train into that, and it's about 5.5 million watts of fixed resistance heating. So as you can see, this is not unlike a baseboard heater or you know, the oven in your house or a toaster oven, an incandescent light bulb. It's just fixed resistance heating. The only difference is it's 480 volts and it's 5.5 million watts of it. So you've got a train that's completely frozen. You fire up all of these heaters and you can see it goes underneath the train, next to the train, all the way down this it's an above ground tunnel, I guess, for lack of something better to call it. So it goes all the way down there at a very slow speed, and as it goes, it's being thawed out by all of this heat. And here's the train inside of it being thawed while I was taking that picture. And they have to be quite careful. If there's rubber hoses or non-metallic equipment on there, it can melt. When I took this tour, by the time you walk halfway down that tunnel, you want to strip all your clothes off because it is just scorching hot. So you have to be careful because they can damage the train. Anything that can melt probably will melt. This is a view of the heaters underneath the train down here, and you know, it's just cord and plug connected equipment, all controlled at 480 volts, which I thought was surprising. I would have thought that it would have been higher voltage for 5.5 million watts of power, or 5.5 MW. So we thaw out the train, and then we unload it. We unload the train, and it goes onto a conveyor system. So this over here on the right is all a big long conveyor. This tunnel here, if I'm not mistaken, is about a mile long. I could be wrong on that, but I believe it's about a mile long. And in the National Electrical Code, we would call this a Class 2 location because it's combustible dust. You have coal dust, which is obviously combustible. That's why we're using it here. And any sort of electrical spark or arc or even heat could create a catastrophic event. Imagine if we had a fire inside of this tunnel. So all of the wiring in here is all rated for Class 2 locations. Most of it's actually explosion proof, although it doesn't need to be. Most of it could just be dust ignition proof or even dust tight. But a lot of times the easiest way to do it is to make it explosion proof as well. Everything in the tunnel has a blanket of filth on it. And when you walk through it, you're actually quite surprised at just how clean it is, considering the massive amount of coal. Again, it's 500 million tons of coal per year, I believe, that goes through that. So you can imagine that it's not possible to keep clean. But if we go back, that's pretty clean, right? Considering what we're looking at here, they do a tremendous job of keeping everything clean. But when you do get a bit closer to it and you can see the warts and everything, everything has a layer of coal on it, which is why the motors are dust ignition proof. They're all rated for Class 2. All of the junction boxes, switch enclosures, everything is rated for Class 2 locations. All of the switches are rated for Class 2 locations. In fact, even this is kind of an interesting one, even the telephones are rated for Class 2 locations. It may be low voltage, but there's still enough power even in a telephone circuit that you could ignite the surrounding environment. So I think it's section 502.150 in the NEC says that even low voltage equipment needs to be rated for the location in which it's installed if it's in a hazardous location. More low voltage stuff here. This is a horn. It also is rated for Class 2 location. That luminaire is also rated. So we unload the train, we put it on the conveyor, and we convey the train over to the burners. Now there's some steps in the middle that I'm skipping over because I don't have pictures of them, and to be quite honest, I'm not an expert at it, but they clean the coal. They run it through a scrubber, they run it through filters, they do all sorts of things, and they take out like 95% of the, I believe it's CO2. They take out the vast majority of the pollutants. Now, coal is still not the cleanest fuel on Earth. Nobody's going to argue that. But they do go through and take tremendous efforts to clean it as much as possible. So once the coal's clean, it's conveyed to where it goes. Well, the next step, of course, is to light it on fire. So what you're looking at right there is right inside the building. We could walk up to that and open that door right there that we're looking at, and that is the fire inside of there. I'm not sure exactly how hot it runs. Obviously it's substantial, but here is where we are lighting the coal on fire, and what we're doing, the coal dust. What we're doing that for is to heat up the boilers, which heat up the water, which fire the turbines, which fire the generators, and we're going to get there. So here we're lighting it on fire, and of course it goes through the chimney, and that's the chimney from the ground. Looking at it again, it's just over 700 feet tall. That's standing at the base looking up the chimney, and this is actually inside the chimney looking up. So at the very top of the screen is the actual ducting where the products of combustion would be transmitted to the exterior, and then inside of it, as you can see here, you've got all these conduits that go up about 700 feet. So I'm sure in accordance with the NEC section 300.19, I think it is, I'm sure that every 100 feet or so they support the conductors inside of those conduits. When you get about halfway up the tower, you can walk out on some little platforms, which I did, and when you're on a little piece of metal and that's the only thing separating you from the ground 350 feet below, I'll be honest, it's a bit unnerving. But when you're walking around inside, halfway up, you've got all of the flashing lights that warn aircraft that they're flying over a tower, and this is what those lights look like. So they're hinged. Normally this would be closed, and you can open it up to change the lamps, to change the electronics, whatever you might need to do. That's all inside of those. So those are what they call the FAA lights, the what is that, Federal Aviation Administration, I think it is. So very highly regulated these lights are. They have all sorts of specifications that they need to comply with. All right, so we light the coal on fire, we heat it up, and we heat it up so that we can heat up the boiler. This massive white thing down here is the boiler, and when I say it's the boiler, it's a very small portion of the boiler. What I thought was amazing again is the fact that it's suspended in the air. So you've got all of these massive rods that suspend the boiler, and these are basically like shocks, giant springs, and they're just all through this building. How do you support a 20 million pound object from the ceiling? Well, with a lot of big thick pieces of metal and springs and everything else that goes along with it. Absolutely mind-blowing when you walk past this and you understand what it is that you're looking at. So we light the coal on fire, it heats up the boiler, we put water inside the boiler, we turn the water into steam, and we use the steam to fire up the turbine generators. This is one of the generators, and this is just kind of a long shot of it. You can see from the size of it that it's quite massive indeed. The nameplate on this guy is, well, it's one of those numbers where I have to check myself and make sure I'm even saying it right. It's 820,000 watts. Right? So 820,000 kW, or 820 megawatts. Just under a billion watts. And the voltage output is 26,000 volts, three-phase. So 26,000 volts times 1.732 is about 45,000. So to determine the current, we would just take the 820,000 kW and divide it by 26,000 volts times square root of 3, and we come up with about 18,000 amps that come out of this generator. Of course, a generator like that runs rather hot, as you might imagine, so we've got cooled water that goes through it, and this is part of the role of the cooling towers that I mentioned earlier. So we've got to cool that water down so that it can cool down the generator, and there is the water return going through it. And the actual generator is this guy right here. You can walk up to it and you can see the windings on it, you can see the brushes. It's absolutely amazing. Now, as you can see, there's a door back here, so it's not like you just walk up there and touch it, but if you wanted to, you could. You can enter that room. There's a light switch in there and everything else. You can go in there and you could touch the generator and get yourself killed if you really wanted to. So that's the generator. It's indoors, so how do I transmit 26,000 volts and 20,000 amps through a building, right? What size wire would you use to do that? Well, the answer is you don't use wire. They don't make wire that can do that. So you use what's called an isophase system, and each one of these here in the photographs, as you can see, we have phase A, phase B, and phase C. That is one circuit. Looking at those three, it's almost incomprehensible. Inside of each of these pieces of metal in these containers, I'm not sure what the material of them is. I'm guessing it's non-ferrous, but I'm not sure on that. But inside of these are hollow aluminum rods, and those are the actual conductors. So this would be phase A. If you're looking back here, it goes all the way through, and looking from the other side, that is that big square piece that you could see from the photograph, and then kind of a duct for those aluminum rods. And like we were saying, that is phase A, and there's three of those, phase A, B, and C. Phase A, B, and C go outside and they feed this bad boy. This is the transformer that takes our three-phase 26,000 volts, 20,000 or so amps, and changes it over. So here's the transformer. This is the nameplate of the transformer. I know you can't read it, so give me just 1 second. So that's the nameplate, made in Pittsfield, Massachusetts. It's a decent chance that my buddy Frank was involved in manufacturing that. And as you can see, it's from General Electric. There you go. 968,800 kVA. So basically a million kVA, or 1 billion watts, 26,000 volts, 21,000 amps. And though we're not missing any decimals, that is legitimately the size of this transformer. One piece of equipment, by the way. It's not 3 individual transformers. It is a 3-phase bank of transformers in one enclosure, that photograph that we just looked at. It is cooled by 28,000 gallons of oil. And when it's full, it weighs in at 1.1 million pounds. So that's how much that generator moves. And it's been operational ever since they set it back in the early 1980s. And they do have a spare one on site, just in case something were to go wrong, so they can move it. I'm not exactly sure what the process is to move a 1 million pound transformer, but they are prepared for that type of event. So we light the coal on fire, we heat it up, we heat the boilers, we turn the water into steam, we steam the generator creates power, 26,000 volts, 20,000 amps, shoots it over to this transformer. The transformer then changes it, because this is the low voltage side of the transformer, the 26,000. It changes it up to, I believe, 500 kV, if I'm not mistaken. I don't have the high voltage numbers here, but it supplies the switch yard, and I'm pretty sure that it supplies it at 500,000 volts. Now, out of the switch yard here, that's where we get into the transmission and we send it to the different parts of the western United States. So that is the process of making the electrical energy. Now, inside of the building, there's all sorts of different cool things. Now, this is the classroom where I teach every year. Nothing really special about this, but just showing the fact that, inside of it there are parts that is just like a normal building, that you might be sitting in right now while you watch it. There are other parts that are not like a normal building. This is one of several emergency system generators. These are each 5 million watts, 5 MW. And there are several of these, and that's just to provide just what it sounds like. That's the emergency generator, your emergency lights, and also your processes. So if this place loses power, if this place has some sort of an outage, which they haven't had in quite some time, it really is an emergency for millions of people. So they need to be operational immediately, and in order to do that, they have a massive amount of emergency system capacity. So you'll be walking through the building and you'll see things like this. You'll see a 5 million watt generator. You'll go through a door and you'll find yourself in a room that they call the snake pit, and a very well named location here. So here you've got cable tray, and it's just a ladder type cable tray, and there are seriously miles and miles of cable tray in this building. Most of it does not look like this, but inside the snake pit there are it looks like this for as far as the eye can see. So all of that is power tray cable, Article 336, and a lot of that is control wiring. There's also optical fiber cables. There's also communications cables, not in the same tray necessarily, but a lot of limited energy circuits in there as well. You might find yourself running into some large motors while you're in the power plant. This is a rather large motor indeed. I wish I had a picture that could show you the scale for the physical size of it, but hopefully you can read that. The horsepower rating on that is 2,050 horsepower. So pretty good size motor. And you've got motors all through the place. Big motors, bigger motors, the massive motors. This one's 500 horsepower. They also try to be as self-sufficient as they can at the facility. So they have all sorts of tools. This is like a fabrication shop that they have on site. As I mentioned, there are miles and miles of cable tray all through the facility. So most of it, a lot of it is 6.9 kV, so 6900 volts, and the rest of it is 480. So a lot of 480 and a lot of 6900 in this facility. Here's just another picture of some hazardous location stuff blanketed in coal dust. This is a very, very common sight as you walk through it. And once in a while you'll bump into something like this. I set my car keys down next to this bolt just so you could get a feel for it in terms of scale. I think the size of that nut is probably 12 inches, 14 inches. So, and these are just all over the place. So why do you have such massive structural metal and hold down bolts? How far do these go down in the dirt? I have no idea. But a lot of this is because of that boiler that's suspended, right? In order to suspend that kind of weight, as you could imagine, you need to have a massive structure to do that. Some of the other interesting things that you'll see: hazardous location heat tape. You'll just see a roll of this laying around that they're getting ready to install. Something that most electricians would never see in their career, and there's just rolls and rolls of it laying around. This is a control room. It's not the control room. You don't go in the control room, right? That's one of the rooms that's off limits. But this is just one of the small control rooms. There are tons of these different things around, and as you can see, it's got all sorts of monitors. This is where a lot of the technicians will watch and basically just make sure that the lights stay on. This is kind of the stuff that I'm into. This is just some medium voltage switchgear. But I couldn't begin to tell you how many pieces of switchgear and switchboards and panel boards and motor control centers are in this facility. It's a staggering amount. Each of these little blue guys up here is something that, if you're not familiar with it, you should be. If you're into the world of the National Electrical Code, 240.67 and 240.87 both talk about it, and that is an arc energy reducing maintenance switch. I'll go over that here in just a minute, but if you're wondering what all of these little blue things are, they have these on every single switchboard and switchgear in the facility, and that's 100% for worker safety, which I think is great. Just a couple of pictures of some motor control centers and panel boards. There are seriously hundreds of locations like this where you could just stand and take a picture, and it is equipment and switchboards for as far as the eye can see, to be honest with you. Hundreds of feet long, and there's dozens of these rooms that are just like this, so they're all over the place. If you're into the NEC, you might be looking at that door thinking that it doesn't comply with 110.26C, and you would be correct, but that section was put in 1974. This building was built after that, so that's why it has some compliance issues there. So it wasn't the door swing and the door hardware, I don't think, were addressed until 2002. So the rule for having an exit at the end of the equipment was there, but the door swing and the panic hardware did not come into the code until quite later. So at least we have a way out. I would love to tell you that the door swings out and has a panic bar, but they'll get there. They've been addressing that over the years. This is some arc flash reduction maintenance switches. So the idea here is, at a power plant, there are a lot of locations where you have to work energized. In most facilities, there's no reason to work energized. If your world is 122.08 and 122.40 and 277.480, there's very, very seldom any legitimate reason to be working energized. It's an OSHA violation, it's an NFPA 70E violation, and it's a good way to get yourself killed. You can shut down pretty much anything, except if you're in a power plant. If you're in a power plant and you shut something down, you might have millions of people that lose power. And how many of those millions of power are depending on their electricity for a life safety function? Shutting off could quite literally kill multiple people. So you have to work energized when you work at a power plant. Now, what do you do if you're working on an energized piece of equipment that will kill you if it blows up, regardless of your personal protective equipment? Take a look at this warning label here. If I'm in front of this piece of equipment, and it's only 480 volts, if I'm in front of this piece of equipment and something goes wrong and there's an arc flash, we have an incident energy of 101 calories per square centimeter. If you're not familiar with what that means, that is a closed casket funeral, unfortunately. And there is no personal protective equipment in the world that's going to save you from a 100 calorie incident. The shock wave from the event is going to kill you. So here's a piece of equipment that I have to work on energized, and if it blows up, I'm dead. So how are you supposed to work on that safely? Well, what you do is you go back over to the equipment and you put the equipment into maintenance mode. And what they have is they have a system. It's a maintenance switch, and when you turn it on to maintenance mode, if anything goes wrong, then the device will open very, very quickly, long before the incident energy even gets to 101 calories. What they have here is they have a relay, and then they also have optical fiber that actually is looking inside the equipment, and if they see a flash through the optical fiber line, it opens it in like less than one cycle. So it takes the danger from death, right, 101 calories. When I put it in maintenance mode, same piece of equipment, it goes all the way down to 4.5 calories, and you can see that that's a significantly lower amount of PPE that's required. We went from instant death, there is no PPE, all the way down to fire retardant shirt, pants, face shield, gloves, safety glasses, hearing protection. This is a little bit old. You can see down on the bottom right, that's from 2010, and that may have been accurate in 2010. I think today in 2019, we'd see a balaclava and some feet protection that would be addressed as well. So that's not a necessarily accurate label anymore, but they're in the process of updating that. It's a massive facility. Doing an arc flash evaluation throughout the whole thing takes years to do. We've also got high impedance grounding systems all through the 480 volt equipment in the power station. And if you're not familiar with a 480 volt, well, with any voltage, with high resistance grounding or high impedance grounding, the idea is that you insert a resistor, and that's what that white thing is here in the picture. You put a resistor in the system at the transformer. So this is a three-phase Y-connected system. There's no neutral. It's a Y system, but there's no neutral. There's a neutral point. The XO is a neutral point, but you don't have a neutral conductor that leaves it. So you don't get 277 out of this system. It's strictly for 480 volt loads. So you put this resistor basically between the earth, the grounding electrode conductor, and the XO point, the neutral point of the system. And because we don't have any neutral loads, we should never have any current going on that wire, right? Why would I have neutral current if there's no neutral loads? Well, the only reason that I would have current going on that conductor is if there was a ground fault. Now, if there's a ground fault on a system like this and it trips the breaker, we could seriously, it could be catastrophic. We could have a loss of life due to a ground fault. So instead of it tripping the breaker, we send that massive amount of current through this grounding resistor, and that limits the current to like 1 to 5 amps, something very, very low, where it would not initiate an overcurrent device. So here is the front of that piece of equipment with the cover closed, and you can see that it's in normal condition. If there was a ground fault, this alarm would go off. The breaker wouldn't trip because the resistance is high enough that it puts the current so low that it could never initiate the overcurrent device. My resistance on this resistor is about 277 ohms. So if it's a 277 volt ground fault going through a 277 ohm resistor, then that would be 1 amp of current, right? I equals E over R. So we have this on front of that piece of equipment, and if this thing moves up to like 1 amp, 1.5 amps, then we know we have a fault. And when a fault happens, instead of the breaker tripping, the alarm goes off. And that allows the electricians to go through and troubleshoot the system and make sure everything stays operational. All right. I hope you enjoyed this. I hope you learned something from it. And again, if you have any questions or comments, please feel free to get in touch with me. Thanks everybody for watching, and I hope you have a great day.